So good evening and a warm welcome to you all. My name is Mark Searcy. I'm the Pro Vice Chancellor for Science at UEA. And I wanted to thank you all for joining us for the second inaugural lecture of the autumn season and our second inaugural lecture in more than a year. Isn't it fantastic to actually be here in person? It's great to have you all back again. And welcome to those of you who are joining us via Zoom and YouTube as well. Thank you for joining us, and let us know in the chat where you're watching from. Saw some people from around Europe in there as well. I'd like to welcome our speaker for the evening, Professor Richard Stephenson, and also the head of the School of Chemistry, Professor Nick Lebron, who will give the vote of thanks at the end. I just wanted to say it's a particular pleasure to be introducing Richard, who was one of the first people that I met at UEA when I came to visit to give a talk here around 2001, which makes us old, doesn't it?
It makes us old, yes.
We always talked about collaborating, but have never actually managed to do it, although Richard's always my first port of call whenever I need to know about, to understand a mechanism. I also had the pleasure of working with the next generation of Stephensons when Richard's son Michael was a colleague in my lab, and he really is a chip off the old block as another excellent organic chemist. So Richard's chemistry journey began in 1972 with an entrance scholarship to Cambridge to read natural sciences, leading on to the award of an MA and a PhD in 1978 under the mentorship of Sir Jack Lewis, FRS, later Lord Lewis. He then moved, I added this, from the dark side to the light, from inorganic chemistry to organic chemistry, by joining the research group of Arthur Birch, FRS, as a research fellow at the Australian National University. But the thrust of the research, the chemistry of stereo-controlled organoion electrophiles, remained the same. This research continued after Birch retired, with Richard taking up positions as an independent research fellow at ANU, and then back in Cambridge as a senior research fellow at Girton College. Richard moved to UEA in 1984 with the award of a prestigious Royal Society University Research Fellowship, which he held for 8 years. He was then appointed to a lectureship at UEA, quickly becoming a reader in 1994. Since then, he's been visiting professor at the University of Caen, Université Paris 6, Université Catholique de Louvain. He presented the Colloque Troisième Cycle, a traveling lecture series in Switzerland, and returned briefly to ANU through the award of a visiting fellowship. Now with this lecture, somewhat delayed by the pandemic, we can celebrate Richard's appointment at UEA as Professor of Synthetic and Pharmaceutical Chemistry, reflecting his now wide research interests, which include double kinetic resolution, asymmetric click chemistry, helicene synthesis for nonlinear optics, anti-cancer compounds, stepping into my area, in association with the local charity Big C, and most recently, natural product-inspired drug candidates for use against neglected tropical diseases, which is part of UEA's Open Lab Africa initiative, a project which almost entirely came from Richard and which he leads. So please join me now in welcoming Professor Richard Stephenson to give his inaugural lecture.
Well, Mark, thank you very much. This is a big deal. We've got lots of people in the room and lots of people on the internet. And I'd like also to thank the Vice Chancellor and the university and the events team for making this inaugural lecture possible for me. Patterns, it's human nature to love patterns, and chemists are human. It's been that way since the beginning of time, and it's still that way now. So even a classic topic like electrophilic aromatic substitution can have papers appearing this year, changing the pattern of how we see that chemistry. But more of that later. Mark's told you my journey. The fascination with chemistry patterns goes right back almost 50 years. And as we go through this lecture, you'll see a number of examples of these patterns, but none of them as old as this iconic image. I think chemists and non-chemists in the auditorium and on the internet will recognize the periodic table of the elements. It's so well known that it's seen in society. Perhaps we don't all recognize that patterns lead to predictions. And the pattern that Mendeleev created was embellished and completed, so-called, in the picture that we see in the textbooks. But in fact, this sort of pattern seeking never ever ends. And even today, new elements are being identified and the pattern of the table extended, and the properties of the elements give a pattern to help researchers in this area find where to look best for new examples. So the periodic table of the elements is an ongoing living pattern. Let's turn back to electrophilic aromatic substitution. Now, the iconography of organic chemistry might not suit everybody. We have a mixture of chemists and non-chemists to speak to tonight, or I have. So we need to redraw it. So here's my attempt at this. These are donut-shaped objects here. These represent the circle of pi electron density which Kekulé proposed in his visionary structure for the benzene ring. And Kuhn Brown, working with his assistant Gibson, not so long after that, proposed some rules which explain how we've substituted donuts, here an electron accepting group pulling electron density out of the donut, directing to the meta position, that's 4 or 8 o'clock on the clock face. But the opposite, written in a green arrow, an electron donating substituent pushing electron density into that ring, that directs to the far end, that's 6 on the clock face, and also to the ortho positions, that's 2 and 11. So there is a pattern there which people have worked on ever since. Well, so to Cambridge. Not donuts now, but horseshoes. Not electron-rich structures, but cationic structures. Positive charged metal complexes, making these now the electrophiles. So everything is reversed. These structures react with nucleophiles, and the nucleophile addition operates under control. So if we put our electron withdrawing substituent at the terminus of the horseshoe, and out there on the internet I saw Bill Donaldson's name. He did this with acyclic complexes, and I'm showing it with cyclic ones. There is now a control effect which pushes the reaction to the far end of the horseshoe. We put our electron donating substituent at an internal position on that horseshoe, unsymmetrically placed. It also directs to the far end of the pi system. So we can see a pattern there too. And other groups like simple methyl group CH3, they block up one side of the horseshoe and reactivity can occur at the other end. And it's possible to lay one directing effect against the other to oppose the block of the methyl group by putting a powerful donor group opposite on the horseshoe. And Pearson, who worked with Birch and later did many actual product syntheses in Case Western Reserve, Pearson exemplified this type of chemistry. And what caught my eye about this was that in all of these reactions, the nucleophile, the green star, adds to the ligand, written in brown, on the opposite face to the face carrying the metal. It is completely stereo-controlled. I later came to call this stereo-dominance. And these control effects, complete stereo control, these are unusual in organic chemistry. A real opportunity, I felt, to do something different. We should just look at these features in more detail before leaving this slide. This first nucleophile addition can add at either end of the horseshoe. They're the same. And so we get two different structures. And these structures are mirror images of one another. That's what the blue line here is representing. So those mirror image structures, if we pick up the right-hand one and flip it over, we'll find that it does not match up properly with the left-hand one. These are non-superimposable mirror images. Chemists call these enantiomers. The same is true with Pearson's system, non-superimposable mirror images. And if you take the metal off, you still have that same effect. So we're able to identify a property called handedness, or in chemistry, chirality, in these types of structures. Now, patterns lead to predictions, and so to Canberra. Working with Birch, I was interested in demonstrating asymmetric complexation of the ligands. Can we use a handed reagent to bring in the metal to just one of the two faces of that ligand? And then that could be elaborated to make the cation by extending out to the horseshoe. And in this example, something different's happening. We can all see it in the pictures. The nucleophile, the star, has added to the position carrying the substituent, the directing group. It's ipso-directing. So if we just quickly review the patterns here, We've seen donor at C1 just now, directs ipso. Switch that to the opposite, an acceptor group. That directs omega to the far end of the pi system. Place the donor at C2, the internal position here. That directs omega. So what would we predict if we were to then switch to an acceptor group? Perhaps it would direct alpha. That was the type of interpretation of patterns and research that was done at the time. So back to Cambridge, to Girton College. And by now, the list of objectives in the center of this slide, this list of objectives is growing longer. Around the world, people were working with metal complexes of different sizes. So there's a pattern here on the left of the slide as well, from just 2 atoms, E to 2, right through to E to 6 and beyond, to larger structures. So we need to be able to understand the directing effects of all the representative substituents in all of the sizes of metal complexes at all the unsymmetrically placed positions and put them all together in combinations to weigh which ones will overcome others when the directing effects are opposed. And in preparation for my research fellowship, I also set myself the ambitious goal of demonstrating in natural product synthesis each one of those directing effects. And in natural products, we find a lot of Kekulé-type aromatic rings. And so it was important to know the directing effect of phenyl groups. It's a new pattern, a new stage of the research. So let's put this electron-rich phenyl group right there in the internal position where we saw the donor substituent. That directs omega, just like the simple substituents. But when we move it to the end of the pi system at the top of the slide, now it directs omega as well. And so it's behaving differently. But we can play the Pearson game down the bottom. Let's oppose that effect with the donor at C2 on the opposite side of the horseshoe, and we can push the reaction in to the ipso position and add a nucleophile to the position where the substituent is. Back to Norwich. These are just a couple of examples of target molecules that we addressed in my group at this time. And this is meritidine. It's a biologically active and relatively small alkaloid. Focus now on the pattern of synthesis design, how organic chemists think about making molecules. We can all recognize, I hope by now, this flat circle of 6 atoms. It's a Kekulé type aromatic ring system. Attached to the top of it here are 2 red oxygen atoms. So let's build those into our building block for the synthesis design. And also on this ring, there is a side arm with an oxygen. Let's add that into the building block for the synthesis design. It's maybe nostalgic for some people in the room, I think. And so we can easily see that we can elaborate out from a simple example to take that pattern out to a much more complicated example, which has been designed to be exactly right to introduce what we need in the target molecule. And therein lies the pathway to synthesis. We've used the metal twice in that synthesis, but we've only made one stereogenic center, one position of handedness within the molecule. Quick look at a second example before we move on to some other patterns. This alkaloid hypeastrine also has a Kekulé type aromatic ring. With a second ring, 5-membered ring fused to it. There it is in the design. Up here, a carbon with 2 oxygens. There, that is in the design. And so we can relate the patterns of structural features in the target molecule to what we need in our electrophiles and our reagents. And in this example, we work back in terms of planning the synthesis using transition metal complexes, work right back to using nature as our handed opportunity to make just the left or just the right-handed form, just one of these pictures in the conduct of that chemistry. Now, I gave you the impression that planning synthesis with metals was straightforward, but actually, it soon became clear that it was very complicated. And with that complexity comes the great opportunity of having a versatile synthetic method. Up the top here, an iterative method from a 4-atom system to 5 as the cation. Add the nucleophile, it's back to 4. Add the cation, and there's the cation again, it's back to 5 again when we activate and add another nucleophile. I'll just say for posterity in the recording of this, somehow, and this has happened before, these arrows have flipped over in the software. So they're pointing in the wrong direction. I apologize to you for that. I put it right several times already in preparing for the lecture. Let's compare this with the alternative, which is a linear sequence. Start with a 6-atom pi system, add a nucleophile and go to 5, activate, but stay with the same size of metal complex by changing the nature of the metal, add another nucleophile, and so on. So these are distinct patterns. The top pattern is the one that would have been used in the Hippiastrian synthesis, for example. And they can be used in sections as they're interspersed within a more elaborate conduct of synthesis. Well, it's time for a new type of pattern. Malcolm Green published in Nature, which is widely regarded as the world's top scientific journal, not just for chemistry. He published a paper about nonlinear optical organometallics. In fact, this was the first organometallic structure to show nonlinear optical properties. I should just lay this out for the general audience as well. Up the top of the slide, we have the typical design. It's an aromatic ring with a donor group pushing electron density in and an acceptor group pulling electron density out. It's a push-pull type of structure. And what Green did to get into Nature was that he replaced the conventional donor group with a ferrocene, electron-rich organometallic. And in that way was able to produce the same pattern, but in a new guise. And so we argued at the time that since we had a great supply of powerful cationic metal complexes, they should serve as ultra good, uber good, I think nowadays we would say, ultra good acceptors. So all we need to do is to add this group in and replace Green's example by an extended bimetallic structure. And that turned out to be easy to do, because Green's use of a triple bond here means we can easily produce a nucleophile. And we've just seen how to elaborate these structures for the natural product synthesis. So just quickly to take you through this synthesis, we can join the nucleophile to the horseshoe under the control of the donor group, ipso addition, and then by removing that donor substituent as an anion, we can regenerate the horseshoe, rebuild the cation, and build our dipole. And indeed this works. I'd just like you to notice the mirror trick again. We can identify just by looking at these two structures that these compounds have non-superimposable mirror images. If you flip this one over, it won't match on that one because the metal will be drawn upwards. And this is technically called planar stereogenicity, or planar chirality if you prefer. And these molecules do work. With the help of funding from Europe, and particularly the TMR program, which joined Norwich to other groups around Europe to study bimetallic organometallic dipoles for NLO, we were able to show, with help from André Persoons in Leuven, that we do indeed see nonlinear optical properties for these structures. And with European money, escaped from Australia and the other side of the world, it was an opportunity to travel around Europe. And I can't show you all the places we went and gave discussions, but here was a visit to Prague to meet the group of Ivo and Irina Stari, leading European experts on helicene synthesis. And if we just zoom in on here, you can see that Stari and I were planning to put accept a donor group of the ferrocene type, Green's donor group, paired up with my types of electrophiles. And this spiral here represents the helicene of Stari's research at the time. In Milan, the Majorana group was working also on helicenes and had already put organometallic carbene complexes at the end. So let's just look at the pattern here as well, in case the general non-chemists in the audience are nodding off at this point. Here's the pattern. On the left-hand side, you can see push-pull on pi systems, but the pi system is a spiral three-dimensional structure, not a plain old boring flat Kekulé-type aromatic ring. And on the right-hand side, there is a surprise, because the right-hand side has acceptor substituents at both ends of the pi system, and yet it still showed nonlinear optical properties. And these patterns lead to predictions. We call the normal situation single dipole, full turn, and the novel situation, double dipole, half turn, because there's one dipole in each half of the helicene. And we were able to show, with work done in Norwich, synthesizing more elaborate structures, that this works really well, and you can get excellent second harmonic generation from these types of structures. And these molecules have handedness. You've seen the single dipole full turn design. What of the double dipole half turn design? They still have the possibility of existing in one or both mirror image forms. And there is an example that was made in Norwich, where on the right-hand side of the screen, where again we got very good second harmonic generation from this design, with an acceptor group at each side of the molecule. To complete this process, and it's still ongoing work, it will be nice to put donor groups so that we truly have a donor acceptor system. Well, Colin, you didn't know this was coming up, but let's change to a different type of pattern now. And Colin Crease, I took your picture from the internet. I hope that's all right. It was on your webpage at Loughborough. Anybody that works with tricarbonyl ion complexes will know that they have 3 characteristic vibrational bands that you can see in their infrared spectra. 1 symmetric and 2 antisymmetric bands. And in polar solvents, on the right-hand side here, in polar solvents, the antisymmetric bands broaden and merge. But the information that's present in those antisymmetric bands, the separation and the contours of those 2 bands, that information is carried through because it contributes to the line broadening of the band you see in polar solvents. And so this collaboration went on after Colin left to take the chair at Nottingham Trent. And actually, there's a bit of a pattern there. You'll see quite a lot of my collaborators have moved to other institutions and taken chairs over the years. That's how life works out, isn't it? And we found that amongst these patterns, there are 2 types of patterns when we put these carbonyl metal groups into different environments. But let's look at a couple of examples. The patterns are not always easy to see. And Colin and Claire introduced me to principal component analysis, a statistical technique that extracts the information that's present in these stacked spectra measured in different mixtures of different solvents into a pattern where they can be read out. And so we have single solvent positions at the extremities of the diagram and mixtures in the middle. There's a clear pattern there. And this works in a lot of situations. So with alkali metal complexes, we are able to resolve different combinations of alkali metal salts in solution, single salts, potassium, sodium, and lithium at the corners of the diagram. Non-chemists out there don't fret about the metals and the salts and all of this. Soak up the diagram, how by using statistics we can extract from the information present, and such a lot of detail and precision about this. And we can see from a crystal structure by Chris Anson why this works so well. The metal is lining up with the orbitals of the metal complex Kekulé-type ring. So it communicates really well its information to the vibrating carbonyl groups. Well, I'm a professor now of synthetic and pharmaceutical chemistry. So I should talk to you more about synthesis, shouldn't I? I've already introduced the idea of stereodominant groups. Mark was kind enough to mention double kinetic resolution in the introduction, so let's turn to that. Helicenes turned out to be a great opportunity for double kinetic resolution. And Rob Stockman, if he's listening on the internet, he emailed me today to say he hoped to, was an expert, and still is, on bidirectional synthesis. So 2 symmetric helicenes are great for that. And we try to make this look a bit more straightforward. If we take a mixture of left and right-handed forms of our starting material, and then impose a sequence of reactions with a handed control to them, then we can get to exclusively, let's say, the left-hand or M form of the product, or alternatively, by different means, to exclusively the right-hand or P form of the product. That's double kinetic resolution. And the ability to do this in the lab and make it work set me thinking. And what it made me realize was that the patterns of synthesis design themselves need to be challenged. So here are the conventional approaches. We have here on the top left a chiral target molecule. And the pattern of synthesis is the logic of retrosynthesis, working back from that complicated target molecule, through ever simpler structures, eventually to cheap starting materials. And then that's implemented in the lab in the reverse direction, of course. And if you just want one hand, the right hand of the target molecule, then you need to intervene. And sometimes people plan to intervene by producing a symmetrical structure and then breaking that symmetry with a handed reagent. Alternatively, you could start with an equal mixture of left and right hands and break that symmetry by making one of those react faster than the other with a handed reagent. A rate race, a kinetic resolution. And there's a big problem with this. It's not so easy to do, not to make it work well, because all the stereochemical recognition, the hand meeting hand in this chemistry, it's all focused on a single step. And you have to work so hard in order to make that perfect, well enough to get a single hand of the target molecule at the end. Compare that with double kinetic or multi-kinetic resolution. Same pattern of design here, but for this process, we interrogate every step to see whether a chiral, a handed intervention, would be possible. And then we would rank those opportunities to intervene in order to choose the ones where we think we have the best chance of success. Perhaps 2 is enough. And then you would work through in the lab in the synthetic direction and check the product. Maybe it's not entirely a single hand. We need to improve it. But we don't need to invest on optimizing these processes. We can introduce an additional chiral intervention, additional handed moment, in order to improve the selectivity of the overall synthesis. Yes, it costs on yield, but it saves a huge amount of time. It's a different approach to synthesis design and a pattern that challenges people to try these things in practice. Well, I'm not going to take the whole lecture in chronological order. In fact, I've already drifted away from that clock. But let's just look at a broader range of patterns. The patterns of genetics here on the left-hand side of the slide are the meat and drink of many scientists, no less on the research park. Some of you will recognize Professor Hotwood, David Hotwood, now an emeritus professor. He and Kevin Booker-Milburn, a colleague who's now left and is a professor at Bristol. Kevin and I got together with David, and together we got a BBSRC grant in order to work on this, chemistry and genetics. And later, with European Community money, Rebecca Goss, now a professor at St Andrews, and I collaborated on this. I'm not going to take you through the whole thing, but one of the nice things that happens in this chemistry are the people that join us. So I can't pick out all my ex-co-workers in this lecture, but this was special because David's fame as the father of Streptomyces genetics on the research park, David's fame was such that he pulled to Norwich from Japan one of the top young people of the generation. Now a professor in Tokyo. And Koji Ichinoshi worked with David and Kevin and me. And then when he went back to Japan and got set up, he invited Kevin and me and one of Kevin's group members that was working on this. The work continued after we'd ended up in different sides of the UK. He invited us back to Japan and set up a lecture tour. So one of the joys of this and one of the patterns is that the travel is a definite advantage. And perhaps we've missed that a bit, folks, in the COVID years. But it's a wonderful opportunity that comes in this lifestyle. That itself is a worthwhile pattern. Well, Interreg money enabled Sean Bew. Hi, Sean, out there. Sean Bew and me to also build a collaboration and run joint research projects. So we were interested in, Sean introduced me to the science of calyx-arene compounds. I'm not going to show much of this, Sean, because it's not all published yet, but we were interested in interactions across the rings. And for the non-chemists out there, these calyx-4 arenes contain 4 Kekule-type flat aromatic rings connected together to make a sort of basket or chalice, if you like. And if you play the mirror game with these, if you have 4 different substituents around the top of that basket, then you end up with 2 mirror image structures. And if you view those from the top, you can see that they're non-superimposable mirror images. We have a clockwise pattern on the left here and an anti-clockwise pattern on the right. And so this is inevitably going to set people thinking. And in my case, it set me thinking again about nonlinear optics. And so together with Sean, we embarked on efforts in this way. Wouldn't it be nice to enter these structures with a handed influence? Wouldn't it be nice to have nonlinear optical effects in this chiral environment, just as we've shown with helicenes and with bimetallic structures? Not all achieved, but it would be nice. And calyx arenes are fascinating structures. They flex, they move, a bit like an origami model. And so we could envisage situations where the dipoles are aligned with each other or where they become splayed out by the molecular motion. And that will change the overall dipole. And if we combine that with interactions across the top of the molecule, we should be able to switch the nonlinear optical properties. Well, there's a Leverhulme fellowship for me to write at some point. We did try Leverhulme, but we should try again. And these Interreg years, Andy, these were joyous years. And look at the smile. You can't, he's masked up, but look at the smile on Andy's face. It's not just a fluke of the photography. Andy and I were running this program together with colleagues in Southampton and colleagues in Normandy, Caen, Rouen, and Le Havre. It brought a lot of students to Norwich and a lot of students to this part of Europe. It built a community. And it made us make projects internationally across the channel. So I'm not going to be able to tell you all of these projects in the few minutes left in this lecture, but I'd just like to acknowledge Phil Page, who's up the top of this slide, because this also gave me a chance to interact with Phil's group. Some of his students were funded by our Interreg money. And Garth Jones and I were able to club together to bring organic and computational expertise to helping us all understand how Phil's organometallics works so well. So here down the bottom is the pattern, non-chemists, if you begin to wonder. Phil's organocatalysts of this generation were adding oxygen atoms. And if you add an oxygen atom to this model, it could be up or it could be down. And those are, in fact, also mirror image structures, and they are different to one another. They are non-superimposable mirror images. So we needed to look for the pattern of how that substrate could approach to the metal, that's what's represented up here, and how the handedness of Phil's beautiful organocatalysts could operate. And here from the transition state calculations that Garth helped me to do, there we can see the oxygen atom lined up on the CN portion, that's here in the organocatalyst, lined up being transferred to a particular face of the ligand. And with modern computational power, once you've established that type of understanding and got those data sets, once you've achieved that, you can start to understand with patterns how that control can be so effective. Why are Phil's ligands some of the best in the world to do this? So there, these patterns, the iconography of this type of chemistry is what I hope everybody in the audience, chemists and non-chemists alike, can come to appreciate. Well, we'll end up with a few odd questions. It's always nice to ask a question in a lecture. I'm not going to ask for a show of hands. Perhaps you can vote on the chat out there in the internet. Can reactions that do not create handedness be used to create handedness? It's like one of these riddles out of Lewis Carroll, isn't it? First, I better explain it to people. If we fuse a 5-membered ring to a 6-membered ring, we might make a left-hand structure or a right-hand structure. But although these are mirror images, you just have to turn this one round around and sit it on top of the other one. These are not non-superimposable. They're superimposable mirror images. And so there's no point in using a handed reagent. It won't have any purpose unless you change the way the system works. So by this modification, we're able to now produce elaborated structures with the fused rings, which are now non-superimposable mirror images. And from this came the first examples of asymmetric click chemistry. And the chemists out here will know, and the biologists, will know that click chemistry has been one of the most widely taken up bond-forming reactions of this decade. But this was the first time it was done in asymmetric form because it doesn't make a chiral structure, a handed structure in its own right. You have to find an opportunity to do this. And we took this on with organometallics again to use the same handed chemistry to desymmetrize this symmetrical diene to produce now the first example of planar chirality, single hand of planar chirality planar stereogenicity, achieved by asymmetric click chemistry. It made front cover of Chemistry European Journal. And these same opportunities, making these 5-membered rings, could be applied to helicene chemistry. So if we were to join into doing this, instead of making mirror image forms of these new hexaacer helicenes, maybe with the right-handed approach, we could make just the left-hand form or just the right-hand form. And since these will be good double dipole half-turn structures, these should be great also for nonlinear optics. Just a couple of patterns to end up with. Mark, you mentioned big C. We've got some pictures here out of biology. A data set involving high throughput screening, 1,600 compounds examined for their biological activity. What are we looking for in this pattern? It's not a Geiger counter. What we're looking for are the outlying positions which show high levels of activity. And we also were able to collaborate with Jesus Angulo. He's now a professor in Spain. And his technique of a special NMR process, nuclear magnetic resonance, produced these types of patterns that can be interpreted to produce patterns that represent how our bioactive molecule identified in the screen interact within its binding site. In this case, in the enzyme ubiquitin ligase, so over here on the screen, related to cancer. So these patterns are useful, and we took some simpler examples, different type of software, but the same approach. Let's put this into its binding site and then use the pattern to see where we have space in the binding site to make the compound different, larger, fit better, potentially bind stronger, potentially be a more powerful inhibitor and change the anti-cancer properties of the system. So it's the visual images here I'm emphasizing and the information you can get from them. Patterns make predictions. Mark, you'll remember our journeys to SUSTEC, and I was invited back by Jing Zhu, a great enthusiast for target molecule synthesis. And we were able to discuss joining my interest in anti-selective synthesis to his group's expertise in total synthesis. Now, nature's very good at this, and nature makes single-handed molecules with ease. But for target molecule specialists, that process in the lab is harder. It's one of the great intellectual challenges of contemporary organic chemistry, as it has been for many years. And with Brexit looming, I was, again, as you mentioned, involved in starting Open Lab Africa. Across the sub-Saharan belt in Africa, there is a tremendous biodiversity. There's also a largely untapped ethnobiological, ethnomedical culture. And with biodiversity comes structural diversity of natural products. So it's like a playground, really, a wonderful toys for chemists. So we started Open Lab Africa with a launch meeting in Arusha in just over 3 years ago now. You'll see myself and Tom at that launch meeting. You'll recognize colleagues from the pharmacy school. I saw Simon in the audience. You're now also roped into Open Lab Africa, so thank you for that. Mark, you always said you wanted to collaborate. Why not on this? And also colleagues from the med school, Kevin and Mark. So Open Lab Africa was looking at target molecules that we might make in the lab. And the same approach I identified before. Here is a natural product from Africa. It's chapelin. Let us lay it into its active site using software to study the patterns. And then patterns lead to predictions. Maybe we could change one of these rings to introduce an extra interaction with this white dot on this yellow surface. Chemisat there, that's a thiol. But it's a new interaction. Perhaps we can use the patterns to design metamolecules and not just have to do it by trial and error. Chemists have come from Africa with support from Open Lab Africa. Here is Barthélemy Unganemi from Cameroon. He's doing here some semi-synthetic work, modifying a natural product that he brought with him and purified from plant extracts. looking together with the med school to find examples which are more bioactive than the starting points. Perhaps what am I love? He also brought samples in which that we found natural products which are new. This one has modest biological effects, but it's a great example. Every time a new natural product is identified, it's a new opportunity. And to identify it, you need the patterns of two-dimensional NMR and the patterns of the logic that allows you to interpret them. It is a major intellectual task to prove de novo what a structure is if you don't know how it came about, if all you've done is pull it out of the bark of a plant from a bush in Africa. All you've done, it's a major task in its own right. Well, I promised you a couple of odd questions along the way. So here's an odd question. Can we make cars out of cellulose? Well, you need new chemistry to even think about doing that. And what we've been able to show is that by chemically modifying the fabric, cellulosic fabrics, which are used commercially to make biocomposites, we can improve the water resistance, the resistance to water uptake by those biocomposites, to such an extent that they might be feasible for use on the external components of motor cars. Innovate UK funded this and brought together with me just the right team at that time to investigate it, all the different techniques, scientific techniques that we needed. And then with translational funding from Ceres, an Agritech funder, we were able to add Heathcote fabrics to this consortium in order to progress from lab scale work to commercial scale work. Heathcote can treat 50-meter rolls of fabric over 1 meter wide in just a few minutes. And so we're translating our chemical process to the commercial scale, sufficiently large amounts of fabric to make prototype components. Let's just go back to an earlier slide. This is almost the last pattern. From curiosity-driven research in the lab, with translational funding, we get to the opportunity to commercialize the work. Universities like this, Nick, it's impact. It's also great fun. And today, the embargo on the press release for the launch of CellExcel, UEA's latest spin-out company, is released. Just by coincidence, happens to have been de-embargoed, if that's a word, today. So we've been able to take this work right the way through, from simple lab-scale experiments to what I hope is going to be a commercial opportunity, which in its own right helps to lightweight vehicles, helps to add components from the sustainable economy, helps to contribute to very topical efforts right now in the UK about combating global warming and having sustainable technologies for the generations to come. Indulge me with just one last pattern. I think you'll agree in the lecture you've seen a great variety of different patterns and how they can lead to predictions and lead to ideas. Chemists love patterns because they give them ideas. Well, my wife's in the audience. Can't have been easy. Living all these years and all these journeys with a companion that, for whom patterns are dreams and dreams are mere patterns. So thank you out there. Thank you to all the past group members and all the past collaborators and present ones. Thank you to the participants on the internet, and thank you for the participants in the room. Thank you for your attention and for turning out tonight to hear about my interest in patterns in chemistry. And Nick, I think I need to hand over to you now in order to take the next stage of the evening forward.
Thank you very much. It gives me great pleasure to give the vote of thanks to Richard on behalf of the school and the university. For those of you that don't know me, my name is Nick LeBrun, as actually Mark sort of introduced me earlier, but I was hiding at the front. So Nick LeBrun, and I'm the head of the School of Chemistry here at UEA. Richard, that was a fascinating lecture. The diversity of your science was really quite striking. You know, Mark mentioned that you started out in inorganic chemistry and crossed over from the dark side. Of course, you didn't quite leave it behind, because you told us early on that you know, you really got into organometallic chemistry and using metal carbonyls as to investigate directing effects and as in asymmetric synthesis. So, I mean, that was a fascinating start. And you know, you worked in a whole range of different things, and nonlinear optics, helicenes was a striking example of the way that you have set up and developed collaborations with a whole range of different kinds of scientists. You know, you've teamed up with other organic chemists, you've teamed up with theoretical chemists, you've teamed up with geneticists. You know, it was interesting to see the connection with David Hopwood and Streptomyces there as well. Right through to the development of a new spin-out company. You know, so your science has encompassed a whole range of things, from establishing the basics of synthetic strategies, directing effects, through to, you know, synthesis of natural products, and through to materials chemistry as well, which is now developing into an impact, to a spin-out company, and hopefully an impact case study for the school later on. And I'd say that you know, one of the things that has also characterized your activities over the years is leadership. You know, you led 2 very successful Interreg grants, which you alluded to a couple of times there, which brought it was a real boost to organic chemistry in the school, bringing lots of students into the school, PhD studentships, and that was, as you said, with Southampton and various universities, a number of universities in Normandy. And then more recently, start initiating Open Lab Africa, which is a really fantastic initiative to, you know, to bring high-level organic chemistry and synthetic chemistry to labs in Africa. So, you know, I think that speaks volumes for your spirit in terms of intellectual curiosity, but also leadership. So, at this point, I would like to open the floor for questions. So, do we have any questions? And of course, we have people on online as well. So, so they are also, of course, welcome to ask questions. And I think Rachel will feed those to me as they come in. But do we have any questions from any of our audience?
We do have some hands up on the chat, and Zoom people, if you could type your question briefly into the chat feed, it will be read out in the room. We can't, for technical reasons, or project the Zoom meeting into the auditorium PA system.
Okay, so whilst they're typing away, we have a question here. Tom? Oh, just hold on a sec. We need the microphone. So we have a student volunteer who's roaming around with the microphone.
Hi, Richard. So you've worked in so many different types of chemistry. Which one has brought you the most joy, and for what reason?
Well, I suppose the most joy has to be a dead heat. The patterns of transition metal control, which was about half of my chemical working life, at a time when it was all new, and contributing what I felt were fundamental insights in that area. I'll leave it for you to judge, but these were patterns and interpretations of synthesis that had not been elucidated before. In principle, should be just as important as the classic studies of aromatic substitution and all the other classic mechanistic studies. So that gave me a huge amount of personal satisfaction. And then I think the second one I'd have to pick at the moment is, of course, Open Lab Africa. And so many people, there's 41 participants showing on the Zoom. That is an opportunity for us, that's the UK university system or other university nations, to really make a difference. So at a personal level, that gives me a huge amount of pleasure. One of the Zoom participants we could see just recently, the images have moved, but Tunmise is out there somewhere in Ibadan in Nigeria, and she's just waiting for her family visa so that she can come to Norwich. And so she will be the third Open Lab Africa visitor when she makes that journey. So Tunmise, if you're able to hear me now, I wish you well with your preparations on your journey. Tom and I are looking forward to welcoming you. And yeah, I think Open Lab Africa has to take the winning stakes for the recent times, yes.
Thanks.
Thank you. Any other questions? Rachel, do we have any from our online audience? One has just come in, great.
Oh gosh, it's got chemistry words in it. I got a U in A-level chemistry.
Don't mention that.
For those of you watching online, this is Rachel from the events team. I just explained to Nick that I got a U in A-level chemistry, so this question has scared me somewhat. Richard can read it on the screen, but I'm going to have a go just for those of you who aren't able to read it in the room with us here. This is Rob. And he says, Richard, excellent lecture, thanks. Whilst the iron carbonyl chemistry was stoichiometric, thank you.
Whole audience say it for us.
Stoichiometric. It has huge advantages in that iron is a widely available metal compared with most catalytic chemistry, which uses rare and costly and often toxic metals. Do you think the aversion to stoichiometric organometallic chemistry, I can say that one, will be influenced by the current push towards more sustainable chemistry?
Well, that was a tour de force. You now get an A in public reading of chemistry. Well, this is a bit of a deep question. I better not spend too long on it, Nick, but the whole point about stereodominance is that the applied control group, Birch called it lateral control, the applied control group overcomes all the other effects. And as a molecule gets more complicated and our target molecules get more ambitious, and we build up these stereogenic centers, these positions of handedness in the structure, it gets harder and harder to maintain the control. And if every time you need to do that, you do it with a catalytic system, whether it's a cheap or expensive metal, the catalyst has to re-recognize the structure on which it's going to affect chemical change. So there's a recognition step every time. And so, Tom, the reason I was so pleased about my chance to be involved in the development of stoichiometric control groups was that the principle should really work. If you put the control effect in once and use it over and over again, then you don't have to have that extra recognition aspect to operate, to perfect, in order to get the control. What about cheap versus expensive? Yes, iron is a cheap metal. Iron carbonyls arguably are dangerous, but it's really the primary carbonyls that are such a problem. And there's not a large data about metal carbonyls as pi complexes causing major health issues. Ironically, we see them used quite widely now in biological chemistry studies, whereas at the time that was completely unknown. And so I think that the cheap metal aspect is something that's valuable, but not that I wouldn't overplay it really. I think that if you're going to put in even an expensive metal and then use it lots of times, by the end of the day, if you recover the metal, it's perhaps paid its worth. But yes, I chose a cheap metal And there were others around the world doing similar.
Thank you. Any other questions? Is that Hans there?
Hello. Thank you so much for a fascinating journey through chemistry in so many different areas. I was quite curious about the asymmetric click chemistry, if it's not too specific. I understand that you take a symmetrical ferrocene molecule and then attach a symmetrical azide. But this second symmetrical molecule could have gone in 2 different places. So how come it only attaches once, and how come it attaches only to, does it prefer which side it attaches on?
Well, 2 different questions there, which is very good because they're linked questions. I won't go back into the slides unless we need to, but if you imagine me as a ferrocene, I know it's a bit of a stretch of the imagination, and you imagine my arms as the alkynes, and you forget that I'm a human being, so my organs, I'm not symmetrical, but my avatar for this purpose is symmetrical. So the nature of this side is different to the nature of that side, not because they're hands, but because the environment around them is the opposite. This and that are opposite environments. This is my front. My front's the opposite way now. So the control aspect of this is possible because when a hand comes in, I might ask for a volunteer from the audience, but I won't. When a hand comes in to recognize one or other of my 2 alkynes, the stereochemical environment is the opposite, one side and the other. So one side can work well and one side can work badly. Now, with regard to the double addition question, a very sharp question, because I showed the audience in the helocene work how that C2 symmetric helocene was just perfect for parallel synthesis, for making 2 reactions happen at the same time. So we were able to do the double kinetic resolution as a 1-pot double kinetic resolution because we were doing the same reaction at both ends of the structure, which was itself a conceptual advantage. With the ferrocene example, one has to be very careful. We were in this work. Adam Wright, who was in the Zoom audience, was very careful in this work. When the second reaction happens, and it does to some extent, if this is the fast reacting hand that the reagent is recognizing, this is the slower reacting hand. So that's why it doesn't dominate. But if it does happen, and it inevitably does, it is doing a kinetic resolution on something which is now no longer symmetrical, but changed in one side. So that kinetic resolution will change the ratio of enantiomers in the final product. So you have to distinguish between stereo recognition and the actual pragmatic outcome of that type of reaction. Double kinetic resolution can get involved in that. And it can make the product more, or it can make the product less pure in what we would call an enantiomeric fashion, more pure in terms of one hand rather than the other for the general audience.
Great, thank you very much, Richard. So, unless there are any more pressing questions, I think it's time now that we close and we say goodbye to our live stream audience. But before they go, I'd like to say thanks to them and, of course, to all of you here in person for attending.
And just before we do turn off the live stream, I can't greet all of you out there, but I've talked a lot about organometallic chemistry, and I'd just like to acknowledge in the audience Bill Donaldson at Marquette University and Simon Lewis at Bath. Caroline, you saw some of your work featured here. I don't know if we can bring up the list of participants rather than the chat, because the little icon to do that has disappeared off the screen. But I'd just like also to thank everybody out there for the different contributions that they've made, but perhaps particularly to acknowledge people whose own professional disciplines overlap with my interests over these years. So thank you guys, everybody.
And of course, one of the few benefits of the pandemic is our expertise in being able to invite people remotely to watch this lecture. So thank you for that, Richard. And again, so thanks to everybody online for attending, and thanks to everybody here for coming along this evening. We can now adjourn into the foyer area for some refreshment. But before we do that, please join me again in thanking Richard for his inaugural lecture this evening. Thank you, Richard.